Okay, everybody, welcome to the Graduate Center Set Theory Seminar. Today we have Davide Leonessi speaking. He's a current student at the Graduate Center, and he came here from Oxford, where he worked with Joel Hampkins, and he's speaking on what came out of that work. So go ahead, Davide.
Thank you, Gunther, and also thank you, Rika, to invite me to this seminar. We're very happy to be first year student here and be able to talk here at home. Today I'll talk about infinite hex, and in particular, I will talk about this work that I did with Joel David Hampkins for my master's dissertation, that then expanded into an article that will soon be published in Integers. Here you have the references. So the game of hex. Some of you might know it. It's a game that has been popularized by John Nash. Technically, it was first discovered by Pete Hine, a Danish engineer, but we prefer to think of the mathematician father of it. And it's a very simple game with very simple rules, in which there are these two players, red and blue, who are playing on this rhomboidal board tiles. And the goal is just basically to join two opposite sides, where of course like the sides are assigned to either player. For instance, this is a play in which blue has won, as you can see. And usually the convention is that red goes first. That's gonna be mentioned. And well, we have some. So this is also a game which is Nash himself described it as connecting topology and game theory. And in fact, we will see some results which are very topological in flavor. This is a classical result about finite hex. Which is that, first of all, any coloring of the hex board exhibits a win for exactly one player. This is even more than any possible play, like even illegal kind of final positions would be won by exactly one player, according to this condition. And in particular, the game is determined, well, actually from the fundamental theorem of finite games by Zermelo. So in particular, the first player has a winning strategy. Now, I'll quickly show these proofs that will also be kind of helpful later on. So for the first...
Sorry, David, can I interrupt?
Yeah.
Okay, so I've never seen the game before. Can you say a little bit more about like what is the significance of the numbers on the token?
Oh yeah, so this represents a play in which the numbers are it's the order of play. So this is.
Oh,
just...
I see.
So the first.
What is so you start playing on any tile?
Yes. So at the beginning, the board is empty, and the first move is by red. And for instance, red plays here, and then blue replies. So the second stone has been this one, and after some 20 moves, this is the final configuration, and we don't need to fill up the whole of the board. This is already like the final. Kind of the final configuration, and blue is joining these two blue sides. And yeah, one important detail is that the corners are assigned to both colors. So you can see the blue here, this tile is touching both the blue and the red boundary.
And can I ask?
Yeah.
Talk about the coloring of the board. That means which corners are that determines the winning position. So basically, how the border is colored.
That's a good question. Right. No, the coloring really is just a placing of the stones on the board. So the boundary is fixed, and yeah, a coloring is just a more general way. Really, what it means is just a way to fill the board with stones. In any way you place where the stones are the pawns, however we want to call them. In any way you can place the stones. Also. So for a coloring, I just mean that I'm just filling up the whole of the board. So this would be a partial coloring now pictured.
Is there any significance to the 1, 2, 3, 4, 5, 6 ABCD that you have there?
That's the usual notation for. It's like in chess, you usually kind of give some kind of labeling of the.
Oh, I see.
Squares. So it's just the way. Yeah, it's the usual notation. No, it's just. Well, in a way, if you like, we can that can be meant to be that we can kind of give it some orientation, some kind of north, south, east, west, which would also be helpful in generalizing this to the infinite case. Yeah, so no, it's just probably would have been clearer just to bring like a physical board game of this, but I hope is it clear now the dynamics of the game?
Yes, I think so. I'm
good. Great. So about proving these results. So for the first result, we want to show that for any way that we play, there's always exactly one player. So to show, first of all, that not both players can win. Well, there is this very neat proof by Mark Schachner, who basically said that if both players win, then we can actually add 5 vertices outside of the board and build K5, which notoriously cannot be planar. A more classical way to prove this result is also by using the Jordan curve theorem, by saying that, well, just by joining when one finds a contradiction in a similar way. I just find that this is literally a one-picture proof. A bit more interesting, I think, also is the proof that at least one winner exists, which was proved by David Kale, which is more graph theoretic. It's not really, it's not as topological as before. So the idea is to take one board which is filled in some way, so a coloring of the board, and augment and consider just the graph that is given by all the edges of the tiles, and augment this graph. So we're not, because usually we would think of the tiles being connected to one another, but now we're just looking at the edges of the tiles. And we augment this graph by adding 4 vertices and 4 edges, which are called north, south, east, and west, as you can see here. And we start a so-called Gale tour, which really is like a path that starts from the southern vertex and goes along these edges on this board. And so to keep always a blue hexagon, so a blue tile on the right and the red tile on the left. Of course, like we can see here at the bottom, it goes along the boundary exactly because we think of the red region after the boundary as kind of being filled with red hexagons in some sense. So here the important thing is that at every every time that how can I say, the path always has always a way to go, because at each vertex has degree 3, and so there will always be somewhere to go in some sense. So it has to go either to the right or to the left, and if a vertex is between all stones of the same color, then simply the path will not reach it, and so on. So in particular, this path will have to continue. And the interesting thing is that this path has to end. I think I go in the next one. So this path has to end in some other vertex, east, north, or west. North, I mean, actually, it's not going to happen because the boundaries, how they're placed. But this actually comes from a small graph theoretic lemma, which is that any path, well, actually, any graph in which all nodes have degree at most 2 is either a point, a path, or a circle, which is very intuitive. And so in this case, since we are starting from a vertex, it has to be a path, because the first node has to have degree 1. It cannot come back to S, and so it has to end at either east or west, or north here actually. And once we see this, then we have that this path following all the stones on the edges of this, which are adjacent to this path, we can see who wins. And in this example, in this play, we have the red wins, and we can see that by going along this path, and see that from the red boundary we get to a red boundary. In the same way, if instead here blue was winning, then the path would have reached west, and we would have seen that there is like a chain of blue stones that go from the blue sides to the other blue side. So these will also be applicable. So this is also, this relies only on the fact that the tiling is hexagonal. It doesn't really rely on, and it relies on the fact that there are the tiles on the corners are assigned to both colors. That's fundamental in this proof. Okay, well, this is clear. And also another very important proof is about the second part. So that the first player has a winning strategy. So this is very famous as the strategy stealing argument, which has been it's an argument that's been used so many times in different parts of game theory. And this was the first instance of it being applied. So look at the empty board. And we suppose for a contradiction that the second player has a winning strategy. Also, by the way, maybe before we start, by the first part, we saw that there are no draws. So, and also by this theorem, which is the fundamental theorem of finite games, that any game of perfect information, which is finite, is determined. We know that either the first player has a winning strategy or the second player has a winning strategy. So we are ruling out the second case. So we say, again, by contradiction, that the second player has a winning strategy. And the point is that the board really looks the same to both players, because we can take a reflection of the board and all the winning patterns for one player get reflected into winning patterns of the other player. In that sense, it looks the same. And so any strategy for one player can be translated into a strategy for the other player. So the point is that the first player can then pretend to be the second player by making a first move and then forgetting about it and just looking at the board as if that move was not there, and then play as with this kind of reflected second player strategy. Then in the end, if the strategy is actually winning, then both players have to win, and that's a contradiction. Now, here the key really is on the fact that having an extra stone on the board is always advantageous in this game. It will never be a disadvantage. Something which is not true, like for instance in chess, where if you have too many pieces on your board, and you can get an easier checkmate, for instance. So yeah, this is enough for finite hex. And I would like you to think of the board of this board as how we can extend it to the infinite case, and it will probably look something like this. It's quite clear that if we want to play any infinite generalization of X, really means to play the same game on the infinite hexagonal lattice. And the dynamics of the game would be very similar. We start from an empty board, and first red places a stone somewhere, and then blue places another stone, and they keep going this way. And if you like, again, I already mentioned before, like the northeast-west orientation, we can think that red really wants to join the northeast edge of the board with the southwest edge of the board, and similarly for blue. So in some sense, we would like red to join the edges at infinity at the northeast and at the southwest. Now, we would like to formalize this concept, because really, of course, there are no edges to be joined. So, before, I would like to kind of develop some intuition about how this game really works. So we can look first at some draws, and that we definitely, some positions that we definitely want to be draws. So for instance, this is we just have these horizontal stripes that really don't go in the correct direction for either player. And so we definitely want this position to be a draw. Another case is this one, the bullseye, in which we have this kind of increasing finite paths that somehow they are arbitrarily large for both players, but they don't really never depart to infinity because they're all finite. So we also don't want this to be a draw, also because it is very symmetric for both players. So saying that one player wins also would mean that the other player wins, and that's something very undesirable. This is another example that could look at the beginning that could be winning for one of the players, because, for instance, if you focus just on the red spiral, we have this double spiral for both players. If you look at the red one, it really goes in all directions to infinity in some sense. So it really is going everywhere at once. But again, if we said that one player was winning, then also the other would be winning, again by the symmetry. So in this, we cannot create a robust enough winning condition to decide who wins here. So we really want this to be a draw. So the intuition for a winning path for red really is that kind of red does something in the middle of the board and then somehow keeps going in the right direction in the first quadrant and in the third quadrant, which are the northeast and southwest quadrants. The formal way to say it is that we can find, we can somehow give an assign, we can find a chain and assign integers to it so that we have a positive branch and an infinite branch of this path by infinite path. And also we don't want to fix a center in the board, because when we start from the empty board, somehow there's no center. We would like a winning condition which is translation invariant. I will also justify this later with more positions. So yeah, we just want that the path at some point enters the first quadrant after doing whatever it wants in the middle and then stays within it, and the same for the third quadrant. And blue does the same with the second and fourth quadrant. Now, an important thing to notice is that for any choice of center, this condition requires a winning path only touches both axes only a finite number of times, because it has to eventually stop touching them and be strictly inside the relevant quadrants. And that's very important to prove the consistency of the well-foundedness, I can say, maybe, of well-definedness of this condition. So this is kind of the key for a winning condition, that it doesn't allow both players to win at the same time. Of course, one could say that when both players win, then it will become a draw, but really that's kind of, yeah, that's just undesirable for a winning condition. So we prove it by contradiction. We suppose that there is some position in infinite hex where both players win. And yeah, this is the observation. They both have to touch the both axes. Here we can fix any center, it doesn't really matter. And for any choice of center, they both have to touch the axis a finite number of times. And so we can consider a finite portion of the board, which looks like a standard hex board, which contains all these intersections and all the finite paths between all of these finitely many intersections. And this is so here we're just containing two finite paths, one red and a blue one. And you can see that we get a contradiction by the finite hex theorem, because we reduce this to a finite game. And also at the same time, we proved this corollary, which is that if a player is on a game, then for any center, that player is also on arbitrarily large finite hex boards, which is exactly this, because it means that also because this contradiction, if you like, also holds for any larger board that is centered at the same center. Now, I'm saying this because it would seem reasonable to consider this as an alternative winning condition, to say, well, I can decide that red wins a given position of infinite hex if for any center, red wins on arbitrarily large finite boards. Now, this turned out not to be well-founded. Well, kind of, this can make sense, but in an undesirable way, because this is kind of a counterexample to the converse of the corollary, the so-called Zen garden. Because in this position, if you consider any given center, so say this center, and you take the axis center at that one, we would have that there is at least one specific red chain that we can label with as a Z chain and say, well, that goes into the first quadrant and the third quadrant. The problem is that for any different choice, for different choices of centers, we get different Z chains. And a key thing is that we would like to have a single Z chain that defines that satisfies the winning condition. Instead, here we have, again, that for any choices, for different choices of center, we satisfy the winning condition in a different way. And we'll see, actually want to show you before this one. And the problem with that is that well, no, actually, no, I didn't want to show you that one. So yeah, that's just undesirable. Right. So another obvious thing is that this winning condition really generalizes the finite hex condition, because we can embed the finite game into the infinite game. So that's also nice because we're trying to generalize that game. And what I meant with this picture is that here we don't have the translation invariance. So that if we consider a center at A, we would say that the red Z chain satisfies the winning condition for that specific choice of center. But then if we move the center to B, then we would say that blue wins. And so one could make an elaborate combination of this one to find something similar to what we had before. And so for any different choice of center, we have that either red or blue wins in the same position. So that's why we need one single Z chain to be winning. Also, this is another example of losing chain, which is less intuitive because we have that the red path somehow goes in the correct direction, northeast, southwest, but then it also always comes back to the center. So in some sense, it never really departs of the infinity. So this is also draw according to the winning condition. And this is also another example of draw in which we have that there is a single connected component that somehow for any different choice of center, for any different choice of center, we can specify a single Z chain that satisfies the winning condition with respect to that center. But again, we have that even though it is all in the same connected component, we are always satisfying the winning condition with a different one. And some people claim that this is not too controversial, but yeah, it doesn't fit well into the picture. But that's also something we're thinking about. Now, to conclude the discussion about this winning condition is about the complexity of this winning condition from the descriptive set theoretic, sense. So we're considering all. So here it's probably clear why I use the word coloring. Just we consider the partial colorings of this infinite hex board, and we want to consider all the colorings that satisfy the winning condition for one of the players. Now, the winning condition is clearly at most sigma 1, where because we can describe it with a second order existential quantifier. So because the condition was there exists a Z chain, so we're describing like an infinite portion of the board, the Z chain, such that a number of conditions are met. So for any origin, we have certain conditions, and then we need to specify that they all it's kind of reasonable to describe it is the first quadrant, third quadrant, and those are all kind of first order quantifiers because we're quantifying on tiles or finite paths. Now, a point is that if well, we could try to prove that it is exactly sigma 1 as a complexity, because there is the problem of ill-foundedness of trees, which is sigma 1 complete. So if we could embed ill-founded trees in the hex board, making sure that a certain position is winning, if and only if it represents an ill-founded tree, then we would be able to say that this winning condition is exactly sigma 1. The problem is that somehow they don't fit. In the infinite branching node is something that is very hard to represent in the infinite text. Really, there is not enough space, because in an infinite branching node really has to be an infinite branch, like somehow a path from which there are infinite many offshoots, and we don't want that infinite path to be winning, and so we have to put it either vertically or horizontally or in some non-winning direction. And so yeah, there are some kind of geometric problems in the density of the tiles. So the next best thing is to say, well, is it Borel? So can we find a sigma 1 condition to say that a position is non-winning? This would be equivalent to saying, well, there exists some kind of blocking pattern in the non-red tiles, so like in the blue or empty tiles in the board, that somehow create a block and make it impossible for red to win. But that also kind of it's very non-trivial to find. Also, because that would imply that then any game starting from a Borel position, which really is like most of the positions that you can think of, are determined. And so because of Borel determinacy, which is a well-known result, provable in ZFC. But also, we'll be tempted to say, maybe is it arithmetic? Maybe we can get rid of all these second-order quantifiers and just describe it with first-order quantifiers. We have this kind of candidate that maybe works, but we still need to think about it. So that we say that there exists somehow a red stone such that for any possible choice of center, that red stone is linked to some red stones in the first and third quadrants, such that from these stones we can always find stones farther out in so from these first quadrant, or there are stones arbitrarily far out in the first quadrant that are linked to this stone. But then we don't know if maybe this condition means that we are just always branching. I'm not sure if Naga was drawing on the blackboard for people remotely. But yeah, that's.
I'm so excited to experience this is.
Sorry?
Oh, sorry. I haven't read my tablet. I can't believe my audio. Excuse me. I've just been taking me 20 minutes to load up Zoom here. And I'm sorry if I interrupted your lecture. Please go on.
Good question. I'm not sure if I hear well. Maybe Gunther.
Excuse me, could you repeat the question? We couldn't quite hear it well here.
Maybe I can show the drawing of this last thing, but it's literally just a sketch, and it's just a possible characterization that we're not really sure that whether it works. So as of now, we only know that the first line, that the winning condition is at most sigma 1, which is kind of the immediate from the definition. So if there are no other questions, I can move on to the title of the actual article, which is that infinite hex is a draw. Which means that both players have a winning, have a strategy so to force a draw. Now, the first observation is that the second player cannot win exactly by the same strategy stealing argument that we used for the finite case. Again, because the board, when starting from an empty board, it literally looks the same to both players. And again, we can reflect it so that all winning patterns for one become winning patterns for the other. So forcing a draw is the best that the second player can aim for. So it has stopped working. Yes. So we define explicitly a second player strategy that we call mirroring strategy, because basically we are pairing tiles above this kind of mirroring axis, if you like, this green line, with the ones below. So here you can see that A0 and A0, A1 and A1 are all around this green axis. And the idea is that, so this is a second player strategy. So whenever red plays on some tile, say A2, then blue will reply with the pair tile to it, which will be A2. And it will be free because of how this pairing works. And the same way, if red plays in A3, then blue plays in A3. If blue uses this strategy from the beginning, then blue will always be able to reply in this way to red attacks. And I show this one because it is key that red somehow cannot cross this green axis in the correct direction, which would be northeast, southwest. But it can only cross in this direction, which is kind of the wrong direction for it. And we'll see that it is the key for the next step, because if we suppose that red has actually won some position, then it means that it has a Z chain that wins. So we kind of go up from positive infinity, we go down, and at some point it has to cross this chain. It has to cross this green line, and it will cross it in this way because blue is playing along according to this strategy. And then if that is the first intersection, then at the same time, blue has built, because it has been playing this mirroring strategy, a corresponding infinite branch that mirrors the one above by red in the positives in the first quadrant. So blue has built it in the fourth quadrant. And then red is simply stuck, because if there is the first intersection, then it cannot come up again out of the green axis, cannot go north again, and it cannot cross the blue path either. And so red hasn't won after all. And this is the contradiction. This is also kind of a slight generalization of the strategy for asymmetric finite hex, which is based on a similar principle of defining some kind of half and make sure that the player that has to join the longer sides wins on an asymmetric board. Now the point is that this strategy really doesn't work if we're not playing from an empty board, because if red somehow starts with 2 stones, maybe red can play them in two paired tiles, and that would break the whole of the construction. So even with 1 extra tile, red could win against the strategy for blue. And so we want to, but we would like to say that still this is such an infinite game that it should not matter what happens so locally, and we would like it to infinite hex to remain a draw, even when finitely many stones are already placed. And there are 3 approaches to solve this conjecture in different ways. So the first one is to keep the same winning condition and assume that blue can construct some obstacles and kind of use these obstacles to somehow create infinitely many obstacles, and we will see it later on. Another way is to make the winning condition stricter so that it's easier to draw. And another is to make the game unbalanced, so to give more power to the winning player, which was the most recent development. And so that's the one that I'm going to talk next. This stems from a question by Timothy Gowers, who asked whether if one player, red, places 2 stones on each turn, does the game remain a draw? Now, the answer is no, because really that's a lot of power for one player. But to get there, we first do a warm-up result by Cameron Brown for the 3-for-1 variation. Maybe I would like to mention before also the 7-for-1 variation, which is kind of the most immediate example, because if we consider this kind of extreme example of 7-for-1, if blue places 1 stone, then red can just kind of circle it up with 6 stones, and then use the 7th stone to build a winning z-chain. And it can do it from a given center and then build it up towards infinity. So that, also, a very important thing is that, of course, in order to win when starting from empty boards, the players have to place infinitely many stones, and we are considering really only plays which last for omega many turns. It does also make sense to consider this game to continue in transfinite time, but we will see that it's not necessary for these strategies. So back to the 3-for-1 variation. So we give red 3 stones to place at each turn and blue only 1. So again, we define an explicit strategy. So red at the outset of the game defines this green diagonal and defines an assignment of tiles, in particular to each tile only to the ones which are adjacent to this green diagonal. So again, to tile B, it assigns C and D, and so that it is like the adjacent tiles on the opposite side of the axis. And now the point is that red wants to construct a path that goes along that remains adjacent to this green diagonal, and so wants to make sure that blue does not cut through this diagonal. And now red has the power to do it, because and we want to say that if blue, for instance, plays in B, then red will play in C and D, so that it kind of creates a safe detour around it and ensures that blue cannot cut across exactly. And also, so it is kind of creating this detour with 2 stones, and then uses the 3rd one to ensure that there are no holes kind of left along. And so it really constructs a winning Z chain in time omega. So here, this is an example of a game where we see that when blue plays next to the green axis, then red plays directly next to it. And when blue plays away from the green axis, then the green diagonal, then red can just ignore it and use all the free stones to build up towards the winning Z chain. The important thing is that each turn, red is placing at least 1 stone to build this winning Z chain. And so here I'm representing them here to say that it kind of grows from the middle towards both, towards plus infinity and minus infinity. And this will be done in omega many moves. And a nice thing is that, as a corollary, is that we could actually start from this position, because really all the red cares of is just a tiny kind of channel of width too to play in. Now, the problem is that if we drop the 3rd stone, this strategy does not work in time omega. It would in transfinite time, because the problem is that if blue from here played arbitrarily far out, then it would force red to kind of follow it along the way. And so we could find ourselves after omega many turns to have a position which is very sparse, right? And so we would, of course, it's very natural to say, well, we can continue playing up to omega squared, omega to the n, and in countable time, actually, we would reach a position which is 1. But we can do better than this. So we can start from this position. So here we're proving for the 2-for-1 variation. Red plays with 2 stones and blue with 1, and red has a winning strategy. This is with referee, because the referee gave us a very good hint on this. And at the beginning, we weren't sure, and then it turned out to work. So basically, we are refining the strategy that we already used. The referee of integers, I should say. And so red still wants to build a path along this diagonal. But the point is that, also I should say that this position, so we can make it so that in the middle there is this channel of width 2 as before, which is as long as we like, and then we have these 2 cones, which it's only important that they have some positive angle, and then of course they can be approximated in some way. Right. So the game should be, most of the times would be as before. So we just have the same assignment of the tiles, which are adjacent to the green diagonal and on the opposite side of the attack by blue. So as you can see here in the middle of the channel, in this channel, it just works exactly as before. The point is that we want to be able to bend this diagonal every now and then. So we would like to also to play in the standard way, also kind of close to the middle of the board. Again, as before. And then the interesting thing is when we are playing far out from the center of the board, so farther than any previous move already played in the given play. Because in that case, red can reply with only 1 stone, bend as in that picture, and use the extra stone to make sure that there are no holes, as we were doing before with the 3rd stone. Now, you can notice that here in the bend, by bending this path, we are ensuring that red can always reply with 2 stones and make sure that blue never cuts across it. That's kind of the key. There's no empty tile next to the green path, which is adjacent to 3 empty stones, because otherwise blue could play there and somehow manage to cross. So this is the strategy. Now I need to just prove that actually leads to a winning condition, to a winning position. So we have that, because the point is that red is using this 2nd extra stone at the cost of bending. We want to make sure that red does this infinitely many times in time omega. That's also important. Now, the point is that at any finite stage of the play, blue has only finitely many opportunities to force red to reply with two stones, because that would be only to the on the tiles which are close enough to the center, where close enough means within the two farthest stones which have already been placed, and there are just finitely many such tiles. And so blue cannot go on for more than finitely many turns to force red to use both red stones. And it's obvious that if blue in the cone plays out far out from the green path, then simply red will use both of the two stones in the middle. And also, blue cannot create threats far out in the cone, because we are considering also those blue stones in saying that red has to play farther out than any previous move by both red and blue. So blue is not creating some strange threats, and by bending, we're always bending the path in a pristine part of the board, so that nothing strange is happening in some sense. Right, so yeah, this is enough to say that red has infinitely many opportunities to bend the path and so create the winning Z chain, and does so in omega 9 turns. Also, a fun corollary is that actually red could also choose to use these opportunities to bend the path only every other time that the occasion arises. So indeed, red can play 2 for 1, but infinitely often elect to play only 1 for 1, which is somehow, yeah.
So instead of choosing to play 1 for 1, they have like some sort of set where they can play 1 for 1, where they ask for 1 for 1. You know about that at all? Or?
Right. Yes. In fact, that's exactly the observation I was saying after. So, if blue decides that red has to play 1 for 1, okay, that models kind of your question, right?
I was thinking more it's just part of the game. If there's some specific subset of it.
Oh, okay. Say like on all odd turns of red plays 2, and okay, every other one. Yes, I've been asked this question, and that could be model of saying, oh, red plays 1.5 stones, if you like. You can kind of think of it in that way. Yeah, it just doesn't work, because red has to reply with 2 stones when blue attacks. So like if blue knows that red can reply with only 1 stone, then just simply blue plays next to the green path, and red can only reply with 1. Sorry?
Works at all,
I mean, this strategy cannot be adapted easily, at least to that case, because really, especially just in the middle channel, if blue plays in the middle channel, then red has to play with 2 stones. So if it is already planned before that, at some point blue will play in there, then there's no way maybe from a different initial position, but then yeah, we would like some, yeah, right. And yeah, so yeah, so more in general, like when someone else, either the rules or blue, decide when red plays only 1 for 1, that's an interesting question. I don't have the answer. In general, also, it would be interesting to consider the n for n variation, because the drawing strategy that I said at the very beginning, actually, maybe I can show you maybe very easily from here. No, I cannot, because I have this. Anyway, if you remember it, maybe it was here. This one, if it was a 2 for 2, in a 2 for 2 variation, this strategy does not work. Again, because red could just cut across one axis, and blue cannot really reply, and so something different would be needed. So already a 2 for 2 case is quite new. Okay, that should be all. Okay, this last section I will summarize more very quickly. This was the extra section, so I think I will have another 15 minutes. More or less, maybe 10 minutes. I will go through it quickly. So this was so here we go back to the finite advantage conjecture, and we try to solve it in the case of the standard game. So with the normal winning condition, we're playing 1 stone for each player. Now, the conjecture, so the assumption that I mentioned before in the 3 approaches, was that we could assume that blue has a first player winning strategy on a board, on a subboard that looks like this, as a trapezoid, where the trapezoid is gotten by truncating an isosceles right triangle. And so blue is in the orthogonal sides and the red boundaries are the parallel ones. Now, notice that the proofs that we gave for finite hex, they mostly replicate also here. So the existence of a winner holds because it is still an hexagonal tiling and the boundary and the corners are always assigned to both players. So the existence of a player works. Not both players can win, again, the same way, logical sense. Of course, this is an asymmetric game, so we don't have the strategy stealing. In any case, yeah, this is first player because it looks like the second player cannot win in any way. Also, this is a conjecture because I actually had a chance to talk to Maciej Brzezinski, who was the then champion of Hex in 2021, and I asked him his opinion on this question, and he said that in general this is a very hard question. Also, yeah, sorry, I didn't define it properly. So not only blue wins on all such trapezoids, but basically for any given short red side, so you say, well, the red side is like 10 hexagons long, we can find a board by like increasing the size, so making the blue sides longer, such that blue wins. In some sense, we can also think of this as pushing the red side far out enough so that blue has a winning strategy. Now, this is also very easy to see for very trivial amounts of for very short sides of red sides, red short sides. And but yeah, it does become very complicated. Right. So of course we can think of this as if blue wins, then blue is creating really like an obstacle, right? In the first quadrant. That's kind of the idea. So the proposition is that if blue wins on such trapezoids, then there's no finite advantage. So the game really does really remain a draw. And we can create explicitly a strategy for this. Also, yeah, remember that by the strategy stealing, the second player cannot win, so we're gonna present a drawing strategy for the second player who's blue. I mean, here it's from a finite position where finitely stones are already placed, so it's not really important if it is a first or second player. So anyway, this strategy can be translated into a strategy for red, so that both players can force a draw. So we focus on blue. And so you can see here very small is some finite position, right? Some finitely many stones have been placed there. Then we fix any center and we consider the axis that results from it. And blue considers these infinitely many trapezoids that contain the two axes that we have. And think of having infinitely many of them, right? They just fill up the first quadrant. Now, the point is that if blue wins on infinitely many of them, it doesn't have to win on all of them, just infinitely many. Then it means that blue has constructed infinitely many obstacles that cut across. And so if red has won, if red ends up winning, then it would have to somehow do a zigzag across them. But if there are infinitely many obstacles, then red would have to zigzag infinitely many times and get out of the first quadrant infinitely many times. And that's, well, of course, would not make it winning. So the way that blue does it is by select the smallest, so kind of the nearest to the center of these trapezoids and activate it and somehow play only there. And plays on it until winning it, ignoring whatever happens outside. And then, which will happen in finite time. And then just selects the next completely empty trapezoid, and there will be some which is completely empty, and continue this way. And so it will end up that blue wins on infinitely many of these trapezoids. And as I said, if red had won, they would have to do zigzag, and yeah, this just wouldn't work for red, and that's enough. And yes, so we would like to go infinite again, and this was the main thing I wanted to say, that this looks a lot similar to this question, right? We could just get rid of the long red side and say, well, can blue win on this truncated quadrant? We just have two. So this is a very asymmetric game because it is because blue would win So this is an open game for blue in the sense that blue can only win infinitely many moves, and red can win. So if blue wins, then blue wins in infinitely many moves. And if red wins, then red wins in infinitely many moves. So it is not open for red, because somehow red has to escape. This is a taste of the angel and devil game of Conway for anyone who has seen it. And right, so this is, and we found these equivalents that if blue can actually win these truncated quadrants, also on all of them, because these are not arbitrarily large, because if blue can win on one of them, then blue can also win on all the smaller ones, just simply because they're contained into one another. That's a minor detail. So if blue can win on all these truncated quadrants, then blue also has winning strategies for all the arbitrarily large trapezoids. The point is that we don't know which of these is true. And the fact is that one proof, so one direction is easy. So if from the trapezoids to the quadrants is quite easy, right? Like because any trapezoid, if we could win on any possible short side on any trapezoid, then we are also winning on the corresponding quadrant. And for the other direction, from the quadrants to the trapezoids, which would look very intuitive, we need a property which we call intrinsic locality, which I think I will have the time to show you very quickly the definition. I do have, should I maybe open to the questions, or I don't know. I can do 10 minutes. Okay, just go through. I'll do a very quick introduction to game values, which are, in order to get there. Right, yes. So game values. We consider, so this is a theory well developed in games of perfect information, which in particular are open, which are defined open, as I've just said, so a game is open when at least when some player can win only infinitely many moves. An example is chess, because you win only if you get to checkmate, and you can get to checkmate. If you get to checkmate, then you've done it infinitely many moves, however that is. So in other words, yeah, it is open because it comes from the topology of the game tree, that the set of winning plays is open. And this is like a similar result that basically any open game of perfect information, where it is open for some player, actually it doesn't have to be open for both players. One of the players has a winning strategy, which is kind of interest, because it kind of makes sense to talk about game values that I will soon just show quickly what they are. I will not give the exact definition, but I'm just saying that they generalize the idea, which is very common in chess, of making two and making three. You have a question?
Yeah, for that theorem, like in a game, can you have draws, or is that a game where one player wins?
So you can so you prove it first without draws, and then you say that the draws are implied, because you can if you have draws, then you can first prove it by say that one player wins and the other player wins if they actually win or they draw, and then you do the proof twice, and so it's very similar as a result. Right, so game values generalize the idea of the mating two, mating three concept. So a position is mating three for a certain player, for white, if white can win it at most 3 moves, whatever black does, for instance. And so more in general, a game value is an ordinal that measures this distance from winning, in the same way as mating 2 is being closer to winning than mating 10. So take an example from drafts, actually. Which is or checkers. Yeah, here in America, actually, it's checkers that many of us have played when as children, where you've got this red and black traditionally pieces which move diagonally and then jump over one another, and then we can go into infinite drafts, which is another work that I've done with Professor Hampkins, and you can have these positions in which, of course, you play on the infinite checkerboard that goes off to infinity, and you can have infinitely many pieces on it. And you can have a position like this one, where you have a black piece at the bottom of this infinite alternating sequence of red pieces, and that they can all be captured in one single infinitely iterated jump for instance. This is possible position. Now, a mating 2 position for in this game would be, for instance, this one, where red is to move. So red goes downwards, black goes upwards. And game value 2 means really that red goes down to A and makes 1 move, which is 1. Then black is obligated to jump, and there's obligated capture, and so has to jump across. And then red makes another move to capture it and makes the second move and wins. So those are 2 moves, and black then loses because black has no legal moves to make. That's the winning condition. The same way this can be generalized to 3. So you say, well, red goes down and then black goes up, has to jump, and red again goes down and black is again forced to jump, and then red captures again. So this can be easily generalized to any finite value. So kind of mating n, if you like. And the other thing I wanted to show you is like what it means to have a game value of omega, which really is a position in which the losing player is the one to move. And in this case, black, who only has this one single piece. And black, with his initial move, has to decide among different positions, all of which have a finite game value. So in particular, of course, black cannot make an infinite jump along this infinite diagonal, out of which there are all these offshoots of finite game values, because it would disappear, because it would just go off the board in some sense. And so it would just lose on the next move. So black really has to stop on one of these squares with these numbers, 1, 2, 3, and so reach position with that game value. And so, yeah, the key is that when a position has a game value, so for instance, omega, then the game really is equivalent to counting down from omega. So in this game, if black decides to go to square 4, it is as if black has to count down from omega and decides to count down to 4. And then the rest of the game is just forced moves if both players play optimally. And so they count down to 3, 2, 1. And then when they reach 0, the open player has won. So when a position has a game value, then the open player is winning, has a winning strategy. And this is also a way to prove the open determinacy theorem, by the way, the Gale-Stewart. So, okay, I think I'll have the time to describe intrinsic locality. So for the game of infinite hex, we say that a specific position which is open for some player, so such that a player can and winning for that player, so that a player can force a win infinitely many moves from that position, is intrinsically local if there is a finite portion of the board such that the winning player can win by just considering that region. So just playing there and only looking at the opponent's replies in that region. So this is an extremely local game, even though. And so we showed that if a position in infinite hex has some game value, by the way, game values can be any countable ordinal in theory, in these very countable games with like countable boards, then it is intrinsically local. And if it is intrinsically local, then of course it can only have a finite game value if it has a game value, because only then the open player can win only by playing in that finite portion of the board, and so the size of that finite portion of the board will be an upper bound on the game value of the game. And we can actually, and so we use this. Actually, yeah, we can see directly the implication that I was mentioning. So, assuming this theorem, we can see that the other direction of the equivalence, simply by observing that any truncated quadrant can be embedded into the standard kind of infinite hex board. And we can see that any strategy for blue in the truncated quadrant can be immediately translated into a strategy on infinite hex. And if blue is winning, then this position is intrinsically local. And so blue, and again, blue can only win infinitely many moves. And since we assume that he's winning, then there is a finite portion of the board that satisfies this intrinsic locality condition. And that portion of the board can be made so to be contained in some large trapezoid. And so yeah, that's that's kind of the non-trivial direction of the equivalence between trapezoids and truncated quadrants. And I think that, yeah, the proof, yeah, I will leave it for another time. So thank you very much.
Right, thanks a lot.
All right, thank you very much for this nice talk and all the great pictures. Okay, so questions. Anyone?
How did you make the pictures?
They were quite artisanal. I was at the beginning, I wanted to do something with ticks, but then I realized that I could do something more, a bit more by hand. It was fun. At some point, I got into, yeah, drawing them directly in PDF. Oh yeah, and with my tablet, I did the ones more hand-drawn. Oh, maybe one thing I would like to add is that also I talked about these game values at the end because the point that not that only finite game values appear really means that somehow the fear of game values somehow it just doesn't really apply to infinite hex because the open games of infinite hex, where it means any game with a given initial position, somehow is not interesting because it has a finite game value. So we don't have that kind of complexity. And so this is inherently a not open game. This is very much a not open game. So yeah, that is also. In fact, actually, we started looking at this game exactly by searching for high game values, which we instead found in infinite checkers that instead exhibits all possible ordinal game values of all countable ordinals can be realized in that game. And in chess, it is conjectured, as you know, yeah.
Maybe I have a little question. I mean, I guess I do understand it, but it is a little confusing still. So with this, I don't remember what you called it, but there's this conjecture where you have this game board where you have blue horizontally and vertically and red going like that. What did you call that shape? Trapezoid?
The truncated quadrant.
Truncated quadrant, yeah. And you said you can't do the strategy copying there because you don't have symmetry. But you have symmetry somehow along the diagonal, but you can't mirror around that because you're dealing with hexagons, right? Is that the?
Yeah, it's so if I get back to, I think it was somewhere here. Yes, yeah, because also because really, like when I said the board looks the same is the formal way to say that the winning configurations can be for one player can be reflecting to the others. And
oh, right.
So the winning configuration, so the winning chains for blue here are all finite. And there's no way to reflect them into infinite paths, which are the winning paths for red. Yeah, in this sense, it's very symmetric as a game.
I see. Yeah, the symmetry worked differently before, where when you flip, the red borders become blue and vice versa, right? And here it wouldn't be.
Yeah,
like
there
okay,
you just take one of the axes of symmetry of the finite board, and it's immediate. And also in the infinite hex board, you can just take the reflection along the vertical axis and just swap all the. In fact, actually, then we also did a generalization to all the games that exhibit these kind of features that we called simple stone placing games, which have this kind of where one of the key features really is that any winning configuration, any winning path for one player has to cross the winning paths for the others. So more in general, you consider a set which you're coloring and you divide it in subsets and just say that the winning ones of one player have to cross all the winning ones of the other. So yeah.
So you said it's like open about n per n, right?
Yeah.
But how you know for n per n?
Right. Yes. I mean, in a way that can also be, yeah. That's kind of the most general one. It's I guess that already when we were saying before, like already 2 for 1, or like alternating. So like 1 point. If you, I mean, it could be interesting to say actually the game 1.5 for 1, so 1 and 2 alternated, and 1 is it really equivalent to 3 for 2? I don't think so. It doesn't quite work. It's not quite the fraction of the, because otherwise, like the 1 for 1 and the 2 for 2 games somehow should look very similar, but they definitely don't. So yeah, there's definitely a lot. It does get very confusing at that point. It's much easier to consider at least one player is playing in the standard way. Yeah, it's especially for a computability theorist, it's I know it's very interesting, I guess. But it's yeah, I will try to look into it, but it seems to be much more difficult to capture. Yeah.
You consider this game with different tiling instead of playing, say, by like squares or triangles instead of hexagons, or maybe even something more exotic? You know, if like anything changes in that case, or is it more or less the same?
Right. So for squares, I can say that actually already if you consider finite hex, unfortunately, squares do not work as nicely as hexagons. So if you play finite hex on a chessboard, it's very boring because it always ends in a draw. Because you can always block the other person by playing next to it, if you like. You can easily define some strategy. So yeah, the connectivity of hexagons is very important, and the fact that you can never block someone. Also, because in a chessboard you can always put a stone directly in the direction in which someone is trying to go, like immediately next to it. Here it's a bit. With the fact that you have like this kind of free connectivity of the, well, actually 6 connectivity for each tile, you can somehow always try to get around attacks, at least direct ones. But yeah, more in general, yeah, I kind of hinted at these simple sum placing games, which are just the most in which you don't even have connectivity, you just consider a set. And you consider subsets of it, which is just a vertex coloring game. And there is actually a general notion of a Shannon game, which is basically you have a graph and you have 2 distinguished nodes. And there is a player cut, so a player short that wants to color some vertices and join the 2 distinguished nodes, and cut that is cutting out the edges to do the opposite, making it possible for short to win. That's kind of, you can see hex as a Shannon game by constructing a suitable graph, and that generalizes to any kind of connectivity that you can desire. There are also other more exotic games that generalize hex in a very unusual way, like Twixt, which have very meshed connectivity. Like they have the connectivity of a knight on the chessboard. So they're like vertices of a 2 for 1 rectangle, and so that they all cross around, and that starts to be very interesting, but yeah, very difficult to capture overall. Yeah, thank you for the question.
Have you ever seen this idea in like higher dimension?
Right. So
I don't know how exactly you do that.
yeah, no, you can actually do that, mostly because so actually in the proof of David Gale that I mentioned in the same paper, that's a proof of the equivalence between the finite hex theorem I mentioned, part of it, between the existence of a player in finite hex and the Brouwer fixed point theorem, which basically uses as a construction, you can generalize hex really with a chessboard, and then you just add the connectivity of all the diagonals of each of these small squares. Oh, I'm drawing on the board, by the way. And then you can generalize this to n dimensions, so to n cubes, to n dimensional cubes. So that makes sense in the finite case to consider. It starts to be a bit fuzzy, maybe like to consider. Yeah, because then we consider n-dimensional space, n-dimensional lattices, which are not just lattices. You also have this kind of diagonal connection that you need to define in some meaningful way, but that's definitely doable. And yeah, I think that the winning condition, I mean, in the finite case, generalizes very naturally because it becomes like just faces of these n-dimensional cubes. And you can treat it in an algebraic way quite easily. Yeah, maybe in the infinite case, maybe it starts to be a lot. Yeah, and I feel like it would definitely be a draw because then the connectivity, I mean, no, it's not so obvious. The connectivity of each possible stone becomes so high. Like, from each stone, you have so many adjacent tiles, so many adjacent stones that you could put. So yeah, it would. But then, also both players would win, right? Already in 3 dimensions, it could be. Yeah, yeah. So you need to find some kind of winning condition that prevents that. You don't want both players to win. So yeah, it could be interesting, yeah, to consider. Yeah, definitely. Thanks.
Maybe in 3 dimensions, you would want them to build planes.
To create a plane. Sorry, no, I didn't get it.
In the n dimension, you have the way they play, so that can't have those people. Like we were saying in 3 dimensions.
Right.
If both players are playing lines, then there's enough space for them to both win.
Yeah.
But if they're using planes, you can't
I
have
like
two.
So consider like many planes, one over the other stacked. Is that the way it is?
Yeah.
Oh, right. I see. Yeah. I mean, there have been like people playing like hexels on the Möbius strip or on Tori. Yeah, also on Tori is actually fun because you can say one is trying to create a circle around one of the generated circles and the other one around the other one. So yeah, anyway, that's in a very far direction. Yeah. No, if there are other questions remotely. Yes. Thank you very much for your questions.
Thanks again for the content. Yeah. I think we don't have a speaker for next week, isn't that right?
No, I think we are. Let me just check. I think the next one is March 17th is the next one that we have a speaker for.
Maybe see what the logic workshop.
Okay, yeah, right. Yeah, we have the logic workshop coming up today in about half an hour, and that will also be broadcast on Zoom on the same meeting
Yeah,
link.
it's Athar, right? Athar is speaking.
Athar, yes.
Yeah, he's a really good speaker, so I recommend.
No, your notice said it was attendance in person, and
No, that's only for Adrian. I think I only said that for Roman stock because he for some reason wanted that.
Right.
see,
Yeah, so the rest of them are going to be.
you think I can get in? Well, I
Yes.
can manage it because my dinner is getting ready.
I see. Yeah, you should be able to join that remotely. The Athar is going to use slides, so it should be
Great.
all right. Yeah.
Okay.
Okay. All right. So that's it for today. See you later, or see you on March 17th.
Okay.
Okay. Bye-bye.
Bye, everyone.